Welcome back. So let's recall, given a linear transformation L from V to W, the range or image of L is the set of all the images of L for every vector in V. When the range is equal to the right hand side vector space, we say L is surjective or onto. Here is a beautiful theorem. Let L from V to W be a linear transformation of a vector space V into a vector space W. Then the range of L is a subspace of W. It is of course sitting inside W. You want to show that it is a subspace of W. If you recall, the subspace requires three conditions: be non-empty, be closed under vector addition, and be closed under scalar multiplication. So let's check. Check that range of L is a subspace using the following steps. First step, you know that L of 0 vector is 0 vector, right? That means this 0 vector OW is in the range of L. It is an image. So it is in the range of L. Therefore, range of L is non-empty. Second, suppose you have two vectors W1 and W2 in the range of L. What does it mean to be in the range of L? There exist vectors V1, V2 such that LV1 is W1, LV2 is W2. That's what it means to be in the range. In the range means you are an image of somebody. You are an image of somebody. Now let's look at L of V1 plus V2. L is a linear transformation, so it respects vector addition. You have LV1 plus LV2. LV1 is W1, LV2 is W2. So L of V1 plus V2 is W1 plus W2. What does this mean? W1 plus W2 is the image of somebody. Okay? W1 plus W2 is in the range of L. That is, range of L is closed under vector addition. Third, let's take any real number R and any W from the range. W is in the range means what? W is image of somebody. That is, there is a vector V in V such that L of V is W. Then, what is L of R times V? L is a linear transformation, so it respects scalar multiplication. R comes out. R times LV is R times W because LV is W. What does this mean? R times W is in the image of L. L of somebody is RW. That's what it means to be in the range of L. That is, range of L is closed under scalar multiplication. Therefore, it's non-empty, closed under vector addition, and closed under scalar multiplication. So range of L is a subspace of W. Now let's consider this recall this example we saw in our previous video. R2 to R2 defined by for vector AB, the output is a plus b comma 0. So that's a 0, whereas the first coordinate is a plus b. Now what is range? Range is a collection of all such vectors. A plus b is 0. A and b can be any real number. Well, what does that mean? The sum will be any real number. So any c comma 0. Alright? Any c comma 0 where c is a real number. Now this set or this vector space is one dimensional. It is spanned by just 1 comma 0, you see, because all you need is any c. So start with c equals 1. Every other thing can be obtained by this vector times that number. So range of L is one dimensional. Here is another example. Remember this example, that is the definite integral of a polynomial over the interval 0 to 1. What is its range? Well, we've calculated this definite integral. Turned out to be a over 3, b over 2 plus c. Okay. So what does this mean? Look, I'm going into R1. R1 is one dimensional. Suppose I take a equals 0, b equals 0, c equals 1. 0, 0, 1. So L of the polynomial, constant polynomial 1 is simply 1. That means once you hit somebody non-zero, you can hit anybody. So L is on to R1. That is the range of L is all of R1. Okay. Here is yet another example. Suppose L is given by multiplication by this particular matrix. What does that mean? L of ABC is A plus C, that's the first coordinate, A plus B plus 2C, that's the second coordinate, 2A plus B plus 3C, that's the third coordinate. All I did was multiply by the matrix to find L. We want to check whether L is onto. What does that mean? For any vector in the right hand side, can it be in the range? That means, can I find ABC such that L of ABC is x1, x2, x3? All right. So let's see. Let's start. L of ABC is all of this. Right hand side is x1, x2, x3. Well, this is a linear system, 3 variables. Constructed its augmented matrix 1, 1, 2, 0, 1, 1, 1, 2, 3. Right hand side x1, x2, x3. These are the numbers we want to hit. Well, try row operations. Assuming my calculations are correct, I get this. Continuing further, I get this. This equals here. Okay. Okay, assuming my calculations are correct, this is what I get, and this is reduced row echelon form. So notice the last row, it is 0, 0, 0. Okay, which means I may not be able to solve. 0, 0, 0 on the left hand side and something non-zero on the right hand side, which means I may not be able to solve. So solution exists only when the right hand side, the bottom case, I didn't want to do that. You have 0, 0, 0 on the left and 0 on the right. That is the lowermost expression. x3 minus x2 minus x1 is 0. You want that to be 0 to be able to solve, which means x3 must be x1 plus x2. x3 must be x1 plus x2. So the range of L, that is, you can solve for vectors where x3 is x1 plus x2. Look at this. x1 and x2 can be any real number. x3 is x1 plus x2. So you can see from here itself, you are going to have two dimension. One in x1 direction, another in x2 direction. When x1 is 1, x2 is 0. x1 is 1, x2 is 0. You get 1, 0, 1. The other one, when x1 is 0, x2 is 1. 0, 1, 1. Alright. Range is two-dimensional with this given basis. What about kernel? You want L of ABC to be 0, 0, 0. That's what kernel means. Whoever maps to 0. Same set of equations, 3 variables, right hand side is 0. If you remember, where did this come from? This comes from here. This comes from here, right? L of ABC must be 0. So this has to be 0, this has to be 0, this has to be 0, which gives you 3 equations in 3 unknowns, ABC. Well, look for its augmented matrix. Use row operations. the same row operations we just saw. Reduced row echelon form looks like this, 0, 0, 0 here and 0. Right hand side are all zeros. What does this tell us? A plus C has to be 0, B plus C has to be 0, which means A has to be negative C, B also has to be negative C, whereas C can be any real number. No restrictions. C can be any real number. A has to be negative C, B has to be negative C. So notice this is actually one dimensional because only C has the freedom to be anything. So it is spanned with bases negative 1, negative 1, 1. C equals 1. Alright. So kernel is one dimensional. Range, if you recall, range is two dimensional. Remember this example. Why is this important? Remember L. It goes from here to here. Range dimension plus kernel dimension. Okay, keep that in mind. All right. By the way, kernel has something non-zero, so L is not 1 to 1. That's a given. Let's look at another example. R4 to R3. So these are row spaces. A, B, C, D goes to A plus B, C plus D, A plus C, R3. This is a linear transformation. Look for its range. Range means somebody who gets hit on the right hand side. Let's say x1, x2, x3 are in the range, which means L of A, B, C, D is x1, x2, x3, which means A plus B, C plus D, A plus C is x1, x2, x3. So you get three equations, four variables. A plus B is x1, C plus D is x2, A plus C is x3. So notice I have three equations, four unknowns A, B, C, D. x1, x2, x3 are on the right, they are fixed. Look for its augmented matrix. Okay, use elementary row operations. Looks like I get something like this. Okay, so here this is row echelon form. It is not reduced because that's not 0, that's not 0. I have reduced it and reduced it further. So now this is reduced row echelon form, assuming my calculations are correct. What does this say? D can be any real number. Why? Because A minus D is the right hand side, B plus D is the right hand side, C plus D is the right hand side. That is A is D plus x3 minus x2, B equals negative D plus x1 plus x2 minus x3, C equals negative D plus x2. No condition on D. Of course no, because there are only three equations. No condition on D. So you have every vector here can be achieved. You see, I have in fact infinitely many solutions. So I have infinitely many solutions. So the range is all of R3. R3 has this as standard basis. I don't have to look for any more. What about kernel of L? L is here. Okay, so remember range is R3. L, what is kernel? Kernel, all those vectors who get mapped to 0. L of A, B, C, D is 0, 0, 0. That is A plus B, C plus D, A plus Z, 0, 0, 0. You get a system and you get an augmented. Use the same elementary row operations. You get reduced row echelon form with these particular conditions. A minus D is 0, B plus D is 0, C plus D is 0. That means D can be any real number. A has to be D, B has to be negative D, C has to be negative D. So this is one dimensional. Kernel is one dimensional. Come on, show me the, there you go. 1, negative 1, negative 1, 1. Okay, let's continue in our next video.